The probe vanishes in an instant, crushed into something smaller than an atom, then smaller than a proton, then smaller still, folded into a point that shouldn't exist. A place where every equation fractures and every law shatters, and the universe itself forgets how to be a universe. There are no screams, because sound cannot form where space itself tears apart. There are no final moments because time has already stopped meaning anything at all. This is what waits at the center of a black hole, a prison of infinite density and infinite darkness. And yet for 50 years, physicists have been unable to agree on whether it truly exists or whether it represents the moment when human understanding simply surrenders. Something is catastrophically wrong at the heart of the cosmos. Deep within the universe exist regions where the laws of physics, those immutable rules we trust to govern stars and atoms and galaxies, dissolve into mathematical nonsense. These aren't distant theoretical abstractions, but real, physical locations mapped by our telescopes. Places where space-time curves so violently that reality itself becomes uncertain. Scientists call them singularities, and they hide behind the event horizons of black holes, sealed away from the rest of the universe, as if nature itself is ashamed of them. The very existence of these forbidden zones suggests that our deepest theories, general relativity and quantum mechanics, the twin pillars upon which we've built our understanding of existence, are fundamentally incomplete. In 1915, mere weeks after Albert Einstein published his revolutionary theory of general relativity, a German physicist named Karl Schwarzschild was serving in the trenches of World War I on the Eastern Front. Between artillery barrages and the horrors of combat, he worked through Einstein's field equations and discovered something Einstein himself had feared. A mathematical solution describing an object so dense, so massive, that it would trap light itself. Schwarzschild found that if you compressed enough mass into a small enough space, the fabric of space-time would warp so severely that it would fold back on itself, creating a boundary from which nothing could escape. He called this boundary a surface of infinite gravitational redshift. We call it an event horizon. Einstein was disturbed by the solution. He published a paper attempting to prove that such monstrosities could never form in physical reality. He was wrong. By the middle of the 20th century, astronomers had found them. Enormous black holes lurk at the centers of galaxies. Stellar mass black holes orbit ordinary stars, and scattered throughout the cosmos are the collapsed remnants of dead suns, each one a wound in the structure of space and time. But the event horizon, terrifying as it is, represents only the beginning of the strangeness. Beyond that point of no return lies something far more disturbing. At the very center, general relativity predicts a singularity, point of infinite density where all the matter that ever fell into the black hole is crushed into zero volume. Not small, but actually zero. Infinite curvature, infinite gravity, numbers that stretch toward forever. When physicists see infinities appear in their equations, it usually means something has gone terribly wrong. To understand why singularities are so deeply troubling, imagine standing on the shore of a calm ocean. You can predict where each wave will break, how high the tide will rise, because the water follows predictable laws. Now imagine the ocean suddenly folding in on itself, waves collapsing into points of infinite height that touch both the seafloor and the sky simultaneously. The mathematics would produce nonsense. The predictions would fail. This is what happens when physicists try to describe a singularity. Every equation breaks. Time, which general relativity treats as a dimension woven into the fabric of space-time, ceases to flow forward. The future and past lose their meaning. Space itself, which should have extent and volume, compresses into a geometric impossibility. Physicists describe this as the point where the laws of physics completely stop working, but that phrase doesn't capture the full horror of it. It's not that we don't know what happens at a singularity. It's that the question itself becomes meaningless. The tools we use to ask about reality, mathematics, and physical law simply evaporate. For decades, physicists comforted themselves with a kind of cosmic censorship. The singularities were there, yes, but they were safely hidden behind event horizons, sealed away where no outside observer could ever see them. The universe, it seemed, had a sense of modesty, covering up its own nakedness. In 1969, the physicist Roger Penrose formalized this idea into the cosmic censorship hypothesis, suggesting that nature abhors a naked singularity, a singularity not enclosed by an event horizon. But in 1991, computer simulations by Stuart Shapiro and Saul Tucholsky showed that under certain conditions, rotating matter might collapse into a singularity that was visible to the outside universe. The censorship might not hold. The universe might be willing to expose its points of infinite madness directly to observation. Whether such naked singularities truly exist remains an open question, but the fact that they're mathematically possible means the foundations are shakier than anyone hoped. Yet even as physicists wrestled with the nightmare of singularities, another crisis was building, one that would prove even more fundamental. In 1974, Stephen Hawking made a discovery that would haunt him for the rest of his life. He applied the principles of quantum mechanics to the region just outside a black hole's event horizon and found something extraordinary and deeply troubling. Black holes weren't completely black. They radiated. Slowly, particle by particle, they leaked energy back into the universe. Over unimaginable spans of time, a black hole would evaporate completely, vanishing as if it had never been. But this raised a problem so severe that it would occupy the world's greatest minds for 50 years. Imagine throwing a book into a fire. The book burns. But according to the laws of physics, the information encoded in that book, the precise arrangement of atoms, the pattern of ink on paper, isn't destroyed. It's converted into heat and light and ash, scrambled and dispersed, but theoretically recoverable if you had perfect knowledge of every particle. Quantum mechanics insists on this principle with religious fervor. The universe never destroys information. It only transforms it. But when Hawking calculated the radiation coming from a black hole, he found it was perfectly thermal, completely random, carrying no information whatsoever about what had fallen in. A black hole, according to his equations, erased information from the universe. The implications were staggering. If black holes could destroy information, then quantum mechanics itself was wrong. The fundamental predictability of the universe, the idea that knowing the present allows you to calculate both the past and the future, would collapse. Physics would become probabilistic, not just in practice but in principle. There would be events with no causes, effects with no origins. The universe would be fundamentally random. Hawking believed the information was truly lost, that black holes represented a genuine breakdown in physical law. In 1997, he made a famous bet with physicist John Preskill, wagering that information was destroyed in black holes. Other physicists refused to accept this conclusion. A community formed around the conviction that information must be preserved somehow, that there must be a way for the information to escape. They just couldn't see how. The radiation came from quantum fluctuations at the event horizon, a place wherein falling matter had already crossed the point of no return. How could information trapped inside possibly influence what happened outside? The debate became heated. Leonard Susskind, one of the pioneers of string theory, engaged in what he later called the Black Hole War, a fierce intellectual battle with Hawking over the fate of information. For decades, nobody could prove their case. The mathematics was too complex, the physics too uncertain. Black holes sat at the intersection of general relativity and quantum mechanics, and those two theories, despite their separate successes, refused to play nicely together. Then, in 2004, Hawking conceded. He announced he believed information was somehow preserved, though he couldn't fully explain how. He paid off his bet with Preskill, giving him a baseball encyclopedia from which information could be retrieved at will, a humorous acknowledgement of his change of heart. But conceding the bet didn't solve the paradox. The mystery of how information escaped remained. But this was only the beginning of the strangeness. As physicists dug deeper into the structure of black holes, they encountered something even more unsettling than the singularity or the information paradox. They discovered that space-time itself, the stage on which all physical events play out, might not be fundamental at all. The clues came from an unexpected direction. Physicists studying string theory, an ambitious attempt to unify all forces of nature, discovered a strange mathematical equivalence. They could describe the physics of a black hole in two completely different ways. One description involved the usual three-dimensional space and time, with matter falling into the black hole and a singularity lurking at its core. The other description was radically different, a theory living on the two-dimensional surface of the event horizon, with no interior at all. These two descriptions, despite being utterly different in appearance, gave identical physical predictions. It was as if the universe could be thought of equally well as a three-dimensional space or as information encoded on a two-dimensional surface, like a hologram. This holographic principle suggested something profound and disturbing. Perhaps the black hole's interior, including the singularity, wasn't truly a place at all, but merely a way of encoding information on the horizon. Perhaps space and time, which seemed so obviously real, so tangibly present, were emergent properties, illusions constructed from something more fundamental. The implications reached far beyond black holes. If space-time could be emergent in one context, maybe it was emergent everywhere. Maybe the universe we inhabit, with its three dimensions of space and one of time, is just one way of looking at a deeper reality that has no dimensions at all, no locations, no duration, just pure information processed according to rules we don't yet understand. In 2019, a series of breakthrough papers changed everything. Physicists, including Netta Engelhardt, Ahmed Almhiri, and Jeff Pennington, showed that when you include certain quantum effects that Hawking had neglected, effects involving the geometry of space-time itself, the information paradox could be resolved. They found that as a black hole evaporates, its interior undergoes a dramatic transformation. The space-time inside develops structures called quantum extremal surfaces, and these surfaces can extend into regions that seem to be inside the black hole, but that are, in a strange quantum sense, actually connected to the outside radiation. They called these regions islands, zones that were simultaneously inside and outside the black hole. As paradoxical as that sounds. As the black hole evaporates, these islands grow, and the information they contain leaks out with the Hawking radiation. The resolution required abandoning the clean separation between inside and outside. Near the end of a black hole's life, the interior becomes entangled with the exterior in ways that defy classical geometry. Wormholes form, not traversable wormholes of science fiction, but quantum connections that thread through space-time in ways that Einstein's equations alone cannot describe. the black hole doesn't have a simple interior anymore. It becomes a labyrinth of quantum correlations, a structure where the usual rules of space, the idea that things are either here or there, but not both, break down completely. These discoveries suggested something revolutionary. Space-time isn't just curved by mass and energy, as Einstein taught us. At the deepest level, space-time itself is quantum, subject to fluctuations and uncertainties, woven from entanglement and information. The black hole interior, that forbidden region where physics supposedly stops working, might not be a failure of our theories after all. It might be the universe showing us what lies beneath the surface of reality. But even as physicists celebrated these advances, they knew they had only pushed the mystery deeper. The calculations that resolved the information paradox still relied on a combination of quantum mechanics and general relativity, a hybrid approach that everyone agreed was incomplete. To truly understand what happens at a singularity, physicists would need a full theory of quantum gravity, a framework that treats space-time itself as quantum mechanical from the ground up. And that theory, despite decades of effort, remains elusive. Which brings us to the Planck scale, the deepest level of reality that physics can currently contemplate, and perhaps the most profoundly disturbing frontier in all of science. In 1955, the physicist John Wheeler proposed a radical idea. He applied the Heisenberg uncertainty principle, which governs the behavior of particles, to space-time itself. The uncertainty principle says that you can never know both the position and momentum of a particle with perfect precision. The more accurately you measure one, the more uncertain the other becomes. Wheeler asked what would happen if you tried to measure distances in space more and more precisely. To measure a very small distance, you need to use light with a very short wavelength, which means very high energy. But if you pack enough energy into a small enough region, general relativity tells you that the energy itself will curve space-time, creating distortions, and eventually, if the energy is high enough, forming a tiny black hole. There's a fundamental limit to how precisely you can measure space. That limit is the Planck length, approximately 1/1,000,000,000 of a trillionth of a trillionth of a centimeter, a distance so small that it makes an atom look like a galaxy. At the Planck scale, Wheeler suggested, space-time would not be smooth and continuous, the way it appears in our everyday experience or even in Einstein's equations. Instead, it would be chaotic, turbulent, a seething foam of quantum fluctuations. He called it quantum foam, and it represented a regime where the very concepts of space and time become uncertain, virtual. Black holes would constantly blink in and out of existence. The geometry of space would fluctuate wildly. Cause and effect would blur. The smooth fabric of space-time that we walk on, that light travels through, that planets orbit in, would reveal itself as an approximation, a calm surface, concealing a roiling quantum sea underneath. For decades, quantum foam remained a purely theoretical speculation, a mathematical curiosity that might or might not correspond to physical reality. Probing distances at the Planck scale would require energies far beyond anything achievable with particle accelerators. It would take more energy to observe quantum foam directly than currently exists in all the power plants on Earth. But physicists found indirect ways to search for its effects. If space-time really is foamy at small scales, then light traveling across cosmic distances might be affected. High-energy photons might travel at slightly different speeds than low-energy ones, arriving at different times from distant sources. The foam would blur images of very distant objects, like light passing through fog. In 2005, astronomers using gamma-ray telescopes observed photons from a distant blazar and initially thought they detected the telltale signature of quantum foam. different energy photons arriving at different times. But subsequent observations failed to confirm the effect. More recent studies using X-ray and gamma-ray telescopes to observe the most distant quasars have found no detectable degradation in image quality, no dispersion of light, nothing that would suggest space-time is foamy down to scales 1,000 times smaller than an atomic nucleus. Does this mean quantum foam doesn't exist? Not necessarily. It might exist, but at scales even smaller than we can currently probe, perhaps precisely at the Planck length and no larger. Or the foam might be structured in such a way that its effects cancel out over large distances, remaining hidden from our instruments. Or our models of how quantum foam should affect light might be wrong. The negative results don't disprove the idea, but they've taken some of the certainty out of it, leaving physicists in an uncomfortable position. They know that quantum mechanics and general relativity must somehow merge at the Planck scale, but they don't know how. And they have no experimental evidence to guide them. But the failure to detect quantum foam has done nothing to diminish the theoretical reasons for believing space-time must become strange at small scales. Multiple approaches to quantum gravity, string theory, loop quantum gravity, approaches that otherwise disagree on almost everything, all predict that the smooth space-time of general relativity is an approximation that breaks down near the Planck scale. The details differ, but the conclusion is nearly universal. Space-time is not fundamental. It emerges from something deeper. In string theory, space-time is woven from vibrating strings and brains, objects that live in 10 or 11 dimensions, most of them curled up so small we can't perceive them. The geometry of space is determined by how these extra dimensions are shaped, and that shape can change, transition from one form to another. What we perceive as smooth continuous motion through space might be, at the deepest level, a sequence of discrete quantum events. Loop quantum gravity takes a different approach, proposing that space itself is quantized, broken into discrete chunks. The smooth appearance of space-time is like the smooth appearance of a photograph, which seems continuous until you zoom in enough to see that it's made of individual pixels. At the Planck scale, according to loop quantum gravity, space is granular, built from tiny loops of gravitational field. And these loops connect to form a network that defines geometry. There is no space smaller than a Planck length, not because we can't measure it, but because it doesn't exist. Geometry itself is discrete. But here's what keeps physicists awake at night. If space-time is not fundamental, if it emerges from some deeper structure, then what happens to that deeper structure inside a black hole? Does it remain well-defined even where space-time becomes singular? Or does the underlying reality also break down, leaving literally nothing, not even the quantum information that supposedly can't be destroyed? The singularity problem isn't solved by quantum gravity. It's transformed into a different question, one that current theories can't yet answer. Some physicists believe that when quantum effects are properly included, singularities will disappear entirely, replaced by regions of extremely high but finite curvature. Others believe singularities might persist, but that their properties will be radically different from what general relativity predicts. Still others believe we're asking the wrong questions, that the very concept of a point in space breaks down in a regime where space itself is not fundamental. And then there are the implications for cosmology. If singularities exist in black holes, they almost certainly existed at the beginning of the universe as well. The Big Bang itself, according to general relativity, started from a singularity of infinite density and infinite temperature. All the matter and energy in the observable universe compressed into a point of zero size. It's the same mathematical pathology, the same breakdown of physical law. But instead of being hidden behind an event horizon, The Big Bang singularity is in the causal past of everything that exists. We emerged from it, which means our entire universe might have begun at a place where the laws of physics didn't work, where there was no physics at all, just mathematical chaos. Physicists hope that a theory of quantum gravity will smooth out the Big Bang singularity, replacing it with a bounce or a phase transition, some process that's extreme, but not infinite. Some models suggest the universe contracted from a previous state before expanding into what we see today. Others propose that time itself began at a specific moment, but smoothly, without any singularity. But these remain speculative. The physics of the very early universe is as uncertain as the physics inside a black hole. What happens next shocked even the researchers who had spent their careers studying these forbidden zones. In recent years, experiments at particle colliders and observations of gravitational waves from merging black holes have begun to test the predictions of quantum gravity in indirect ways. When two black holes spiral into each other and merge, they emit ripples in space-time that carry information about the collision. The precise pattern of these gravitational waves depends on what happens at the moment of merger, when the two event horizons touch and the physics becomes maximally extreme. Measurements from LIGO and other gravitational wave detectors have so far matched the predictions of general relativity perfectly, even in these violent conditions. But physicists are looking for tiny deviations, subtle differences that might hint at quantum effects. If the interiors of black holes are not smooth, if they contain fuzzballs or firewalls or quantum foam, it might leave an imprint on the gravitational wave signal. So far, nothing definitive has been found, but the search is just beginning. Meanwhile, theoretical physicists have been exploring what might replace the singularity if quantum effects are properly included. One proposal, the fuzzball hypothesis, suggests that what we think of as a black hole interior is actually a densely packed ball of quantum strings, each one carrying a tiny piece of the information that fell in. From the outside, it looks like a black hole with an event horizon and a singularity. But if you could somehow peer inside, you'd find not a point of infinite density, but a complex, highly entangled quantum state, stretched out over a finite volume. The information isn't lost because it's encoded in the precise configuration of these strings. Another proposal, the firewall hypothesis, suggests that the event horizon itself might not be the smooth, unremarkable surface that classical theory predicts. Instead, quantum effects might create an incredibly hot, energetic barrier right at the horizon, a wall of fire that would incinerate anything trying to cross it. This would violate the equivalence principle, the idea that free fall should be indistinguishable from floating in empty space, one of the foundations of general relativity. But it might be the price we pay for preserving quantum mechanics. The information wouldn't fall into the black hole at all. It would be destroyed and encoded in the horizon before it ever crossed. These ideas are controversial, and the physics community remains deeply divided. Some believe the fuzzball picture is correct. Others favor firewalls. Still others think the true answer will be something no one has thought of yet. What they all agree on is that the classical picture of a black hole interior, a smooth journey from the event horizon to the singularity, cannot be the whole story. The forbidden region is even stranger than we thought. And this is where the story takes a darker turn. Because if our theories break down at singularities, if space-time itself dissolves into quantum foam at the Planck scale, it raises an unsettling question. How much of what we call reality is even real? The objects we interact with every day, tables and chairs and planets and stars, exist in a space-time that we now understand is merely an approximation. The distances between things, the passage of time, these are emergent properties, patterns that arise from a deeper quantum reality that has no space and no time. Physicists sometimes use an analogy to thermodynamics. Temperature is a property of matter that seems fundamental. Hot things feel hot, cold things feel cold. But temperature isn't fundamental at all. It's a statistical property that emerges from the random motions of atoms. At the level of individual atoms, there is no temperature, just kinetic energy. Temperature is something that appears only when you zoom out and look at large collections of atoms. Space-time might be like that. At the deepest level, there might be no space and no time, just quantum information being processed according to rules we don't yet understand. Space and time emerge only when you zoom out, when you look at the collective behavior of vast numbers of quantum degrees of freedom. If that's true, then the forbidden regions inside black holes and at the Big Bang aren't places where physics breaks down. They're places where the approximation breaks down, where you're trying to apply macroscopic concepts like space and time to a regime where those concepts don't exist yet. But this raises a genuinely disturbing possibility. If space and time are emergent, then they can also vanish. Just as temperature becomes meaningless if you try to apply it to a single atom, space-time becomes meaningless in regimes where quantum effects dominate. Inside a black hole, approaching the singularity, space-time doesn't just curve, it evaporates, dissolves back into the quantum information from which it was constructed. The singularity isn't a place where the curvature becomes infinite. It's the boundary beyond which the concept of place stops making sense. And we have no language, no mathematics, no conceptual framework for thinking about existence in the absence of space and time. How do you describe where something is when there is nowhere? How do you describe when something happens when there is no when? These aren't just practical problems. They're philosophical ones, questions about the nature of existence itself. For a being falling into a black hole, if such a journey were possible, the experience would be surreal beyond comprehension. Approaching the event horizon, time would dilate relative to the outside universe. Clocks would slow. Light from the outside would blue shift, becoming more energetic. But according to the equivalence principle, the infalling observer wouldn't notice anything special at the moment of crossing the horizon. It would pass by unremarkably. Only later, heading toward the singularity, would the strangeness begin. Tidal forces would stretch the falling body, pulling it apart in a process physicists call spaghettification. But if the fuzzball hypothesis is correct, the interior wouldn't be empty space at all. It would be a dense tangle of quantum strings, a place where the usual rules of motion and location don't apply. If the firewall hypothesis is correct, the observer would never make it past the horizon at all, incinerated by quantum effects before crossing. And if space and time truly are emergent, then somewhere in that descent, before reaching the singularity, the very concepts of position and duration would start to fray. The observer would find themselves in a region where being somewhere and somewhen stops being a meaningful description of reality. This is the final horror of the forbidden region. It's not just that the laws of physics break down. It's that reality itself, the stage on which physical events play out, ceases to exist. And yet, from the outside, the black hole just sits there, a dark sphere in space, giving no hint of the madness within. The holographic principle suggests that everything happening in that interior is somehow encoded on the surface of the event horizon. That the forbidden region isn't really separate from the rest of the universe, but is just another way of looking at the same quantum information. If that's true, then the singularity is visible, in a sense, to anyone who can read the quantum state of the horizon. It's hidden, but not gone. like a compressed file that contains all the information, but in a form that's unrecognizable until you decode it. The most shocking revelation is still unfolding. Recent calculations suggest that space-time might not just be emergent, but also fundamentally entangled. Quantum entanglement, the spooky connection between particles that Einstein famously distrusted, might be the building block from which space itself is constructed. Two regions of space are far apart because they're not entangled. They're nearby because they are. In this view, the geometry of space, the distances between things, the very notion of location, all emerge from the pattern of quantum entanglement in some more fundamental theory. A black hole interior is strange, not because it's a place where physics breaks down, but because it's a region with a radically different entanglement structure from the outside universe. The singularity is the point where the entanglement pattern becomes so twisted, so complex, that it can no longer be interpreted as a location in space. This interpretation makes a stunning prediction. If space-time is built from entanglement, then it should be possible, principle, to create space-time where none existed before. In the laboratory, using quantum systems, physicists might be able to generate small patches of emergent space-time, regions that have geometric properties, even though they're really just quantum information being processed in a particular way. Such experiments are far beyond current technology, but they're not forbidden by any law of physics. We might one day be able to build a tiny piece of space in a computer, encoding it in the entanglement of qubits, and observe its properties. It would be space that didn't exist in our universe, but in an abstract quantum information space. And yet, it would curve and flex and behave according to Einstein's equations. The forbidden region would become accessible, not by falling into a black hole, but by building one from scratch out of quantum bits. And what would we find if we succeeded? Would we see a singularity form as we add more and more entanglement, packing more information into our artificial space-time? Or would we find that the singularity never actually appears, that it's an artifact of our incomplete theories, smoothed out by quantum effects that we can only barely glimpse? The answers might tell us not just about black holes, but about the universe we inhabit. If singularities are real, then the cosmos is fundamentally unpredictable, containing points where the laws break down and anything might happen. If singularities are illusions, then the universe is more comprehensible but also stranger, woven from quantum information in ways we're only beginning to understand. But there's another possibility that almost no one wants to consider. What if there is no resolution? What if the forbidden region really is forbidden, not just to observation, but to understanding? What if the singularity represents a genuine limit to scientific inquiry, a place where mathematics itself fails because the universe isn't fundamentally mathematical? We've grown accustomed to the idea that nature follows rules, that the patterns we see can be captured in equations. But that might just be true in the regions of space and time, where matter is sparse and gravity is weak, the calm suburbs of reality where we happen to live. In the extreme regimes, at singularities and the Planck scale and the Big Bang, the universe might be genuinely lawless, not because we don't know the laws, but because there aren't any. Physics would then be an approximately true description of an approximately well-behaved cosmos, useful in most places, but fundamentally incomplete. 50 years after Hawking discovered his paradox, 70 years after Wheeler proposed quantum foam, a century after Schwarzschild found the first solution describing a black hole, we still don't know what happens in the forbidden regions of space. We have clues, hints, mathematical structures that might be pointing toward a solution, but we don't have a theory. We don't have consensus. We don't even have a clear idea what kind of theory would work. The black hole interior remains one of the deepest mysteries in all of physics. A place where our two best theories, general relativity and quantum mechanics, both of which have been tested to exquisite precision in every other domain, give contradictory answers. One of them must be wrong. Or perhaps both are approximations to something deeper. What keeps physicists searching, despite the decades of frustration, is the conviction that the universe is comprehensible, that the patterns we see are reflections of underlying order, and that if we're clever enough, patient enough, we can uncover that order. The forbidden region is challenging us, daring us to figure it out. It's showing us the limits of our current understanding, pointing to where the next revolution in physics must happen. Every great advance in science has come from confronting phenomena that didn't make sense, from taking seriously the places where the theories broke down. The orbit of Mercury didn't fit Newtonian gravity, which led to general relativity. The spectrum of black body radiation didn't fit classical physics, which led to quantum mechanics. Now, black holes and singularities don't fit our current theories, and they're pointing toward quantum gravity, whatever that turns out to be. In the end, the forbidden region of space might be the most important place in the universe, precisely because we can't fully understand it yet. It's the crack in the edifice of physics, the place where the light gets in. And when we finally solve it, when we finally understand what happens at a singularity, what's really inside a black hole, what space-time looks like at the Planck scale, we won't just have answered those specific questions. We'll have discovered something fundamental about the nature of reality itself, about what exists at the deepest level, about what it means for anything to exist at all. The universe has been hiding a secret from us, locked away behind event horizons and buried in the noise of quantum fluctuations, a secret about what space and time really are, and whether they're even real. The forbidden region is the keyhole through which we might glimpse the answer. We just need to figure out how to look through it without being destroyed by what we see. And that search continues. In the equations of theoretical physicists, in the data from gravitational wave detectors, in the observations of distant black holes slowly devouring their surroundings. Somewhere in that vast accumulation of knowledge, the answer is waiting. We just don't recognize it yet. What else is still out there, hidden in the mathematics, encoded in the quantum information that makes up the cosmos? What else don't we know? What other forbidden regions exist, not in space but in the abstract landscape of possible theories? Places where the equations break down and new physics must emerge. The black hole singularity is probably not unique. It's probably just the first and most obvious example of a whole category of phenomena that lie beyond our current understanding. There might be other pathologies in space-time, other limits to physical law, other boundaries where reality itself becomes questionable. And out there, at the very edge of the observable universe, light that's been traveling for nearly 14 billion years finally reaches us. Light from a time when the universe was young and small and unimaginably hot. Light from very close to the Big Bang itself. If we could push our telescopes just a little farther, look back to just slightly earlier times, would we see the moment when space and time emerged from whatever came before? Would we see the quantum foam directly? The seething chaos from which order crystallized? Or would we find that the beginning, like the singularity at a black hole's center, is hidden from us by some fundamental limitation, some cosmic censorship that prevents us from ever seeing the origin? These are the questions that haunt physics today, the mysteries that drive researchers to spend careers exploring the forbidden regions where everything we know stops working. They're searching not just for answers, but for better questions, for the conceptual frameworks that will let us think clearly about phenomena that our minds didn't evolve to comprehend. And perhaps the most profound lesson of the forbidden region is this: the universe is under no obligation to make sense to us. It doesn't care whether we can understand it. The fact that we've been able to figure out as much as we have, that general relativity and quantum mechanics work as well as they do, might be a kind of miracle, an accident of our particular location in space and time and energy scale. The regions where those theories break down might not be flaws in our understanding. They might be the universe's way of telling us we're reaching the limits of what minds like ours can grasp. Or they might be invitations, challenges to push further, to think harder, to imagine possibilities that currently seem impossible. We won't know until we try. And somewhere, in the darkness at the center of a black hole, in the quantum foam at the Planck scale, in the first instant after the Big Bang, the answer is waiting, patient and immutable and utterly alien, ready to revolutionize everything we thought we knew about existence itself.